Good morning, everyone. In today's class, we'll just start our optical fiber. In today's class, we are starting the optical fiber. What is actually the meaning of optical fiber, and how these optical fiber have been classified depending upon the propagation of signal, and what are the different types of optical fibers, and what are the applications of optical fiber, and how this optical fiber is actually working, right? So now this actually will discuss in today's class. So we'll just start with the first one, that is optical fiber. So we say that optical fiber or fiber optics is actually the medium, and the medium of transmitting the light pulses along the glass or plastic, right? So this particular phenomena is actually can also be defined as a medium, a transparent, a dielectric medium, which will transfer the signal from one end to the other end, right? With the signal in the form of a light, either that light will be visible light or infrared light. Now, see optical fiber, how this optical fiber, now this is the definition, right? So we understand what is act. Now we have the information, right? How, what is actually the meaning of optical fiber. Now, previously, we used to have the usage of the conventional copper wire. So in the conventional copper wire, so we had the signal, the information, right, in the form of a signal will be transferred, right, from one end to the other end, and the basic phenomena in which the copper axial cable is used as electromagnetic interference, and which will we have to retransmit that particular signal, and how this particular conventional copper wire is compared with the optical fiber. And when we compare this optical fiber with the conventional copper wire, so for transmitting the signal, we are having a lot of applications, right? And the cost of the optical fiber is very less when compared to copper axial cable, right? That actually we are going to see, right? So now this information is enough for us to know what is actually fiber optic system, where actually you are using the fiber optic system. So the communication system that uses light as the carrier of the information from a particular source, right? And through a glass or plastic or a fiber cable is known as fiber optic system. And this information, which is carrying a capacity of communication system, is actually proportional to the bandwidth. So here we need to understand what is actually the bandwidth. So we'll discuss this in very much detail now. Now, when we compare this fiber optic communication when compared with the metallic cable, you can just see this schematic diagrams where you can just see that comparison of the fiber optic and the metallic cable, which is used for the communication network. So here we have just given you the information how this metallic cable and fiber optic cable look like, right? So now the bandwidth of the single glass fiber will be very much higher. So now we need to first of all discuss the uh, differences between the normal coaxial cable and what is the need of studying this optical fiber with respect to the copper axial cable. So now the optical fibers are made of either glass or plastic, so the external electrical noise and the lightning do not affect the energy in the optical fiber when compared with the copper coaxial cable. Now, with this, we can say that there is a transmission of signal with the with the restriction of noise, right? That is possible in the optical fiber, and we had this particular obligation in the coaxial optical coaxial cable. So this is being overcome by the optical fiber. Now, the elimination of crosstalk is very important aspect. This in the normal coaxial cable, you find that there is a crosstalk. So in the metallic cable, we say that there's a metallic cable. There is a crosstalk. Means what is the meaning of crosstalk? Someone is talking to you. So from a phone call,
and another person will again, another person who is talking to the third person, right? So that particular talk will be mixed with your call, and we'll say that is called crosstalk. Now this is in the metallic cable. This was the routine, what the routine disturbances which has been caused when we use the copper axial cable for communication network. So the elimination of the crosstalk is also possible when if you use the fiber optic cable. So in the when we compare the weight and the size, so you can just see that the optical fiber is very small in size when compared to the coaxial copper cable or metallic cable. So and the cost, see, the cost of the optical fiber is very less when compared to the metallic cable. So you can just see we just use silicon dioxide is used to make this optical fiber, and this silicon dioxide is most abundant material which is found on the surface of the earth. That is the reason that we say that is a lower cost, right? And when we go for security, fiber optic cable are more secure than the metallic cable. So why we are discussing this particular phenomena? See, we just started with the definition of the optical fiber, and what is the basic difference, right, of the optical fiber with respect to the metallic cable. That differences we just studied. So if you can just study 4 to 5 differences, I think that that is feasible for you in the examination. We will ask you uh, distinguish or differentiate the uh, differences between the normal coaxial cable with respect to the fiber optic cable. So security is here. The fiber optic cable is more secure when compared with the metallic cable, and safety. See, so here the potential hazards, short circuits, and also the lightning system. If you have and some um, what's water havoc also that can be uh, minimized with respect to the copper metallic cable. So optical fiber is a very greater safety and corrosion. And corrosion also is an important aspect. So due to environmental extremes, there is a possibility of uh, corrosions, and fiber cables are more resistive to this environmental extremes, and they can operate to a large temperature when compared to the normal metallic cable, right? Like this, you are having a longer life and easy to maintain. A longer lifespan of 20 to 30 years is predicted when compared with the normal conventional cable. So that is 10 to 12 years or 15 years. So you can just see the differences, right? Why? See, whenever you are studying something, right, you need to understand what is the definition of the topic what we are going to learn, and then why this particular thing is important, right? If we can compare, we can just compare with the other aspect, so that's such that we can just easily learn. So what is the need of studying this fiber optic cable? So we just compared it with the normal coaxial cable, and we conclude that this particular part, so you can just see this what is actually the fiber optic cable construction of the fiber optic cable. So in the fiber optic cable you find that there is a core, right? So core and cladding, so particularly coating, and then you have a fibers and then cable jacket. So the core is the basic right, the medium where the signal will travel. Cladding will be the outer surface, and always the refractive index of the core should be greater than the cladding, right? So now, so this is the different configuration in the cable. This is you can see that a, a core will be there, cladding is there. Just now we just discussed, and a jacket will be there, which is that is called buffer jacket. So now based upon this different types of optical fibers, you can make the optical fibers either from plastic or the glass, right? You see this is the glass core, right? So which is having the diameter of 0.001 and so on. So having very low signal loss, less affected by the radiation, and which is used for the medical application. Now this is the glass core with the glass cladding. Now based upon the mode of transmission, right? So we divided the optical fiber into single mode fiber. So what is the meaning of single? See, what is the signal which will travel inside the optical fiber? So what is that signal? It is a light signal. So if only one signal is there, one path of light is passing, and which is having a diameter of core is 7 to 10 micrometer, So definitely, and the bandwidth, see every signal, see this is a communication language. So you'll have a bandwidth, and depending upon that bandwidth, the light ray will travel, the signal will travel. So it has a bandwidth of 40 gigahertz. So mostly this particular long distance and low cost circuit like TV cable. So this single mode optical fiber can be used for television cable. And so multi-mode optical fiber. So here the light will you can just insert the two different parts of the signal, and the diameter of the core is from 20 to 100 micrometer, and this is used for medium distance and for high bandwidth. So here why we call this step index optical fiber. So what is that index profile? There's a depending upon the what you can say refractive index. The optical fiber has divided into two categories: the step index optical fiber and the graded index optical fiber. Here you can just see the schematic diagram where you can just see that there is N1 and N2. N1 refers to the refractive index of the core through which the light signal will travel. So and N2 is the refractive index of the cladding. So you can just see step index have uniform reflective index of core. Core have bigger refractive index when compared with the cladding, and you can just see that differences of schematic diagram with respect to the distances and the refractive index, right? So gradient index optical fiber, the core of the gradient index optical fiber is not uniform. So what is the meaning of this non-uniform, right? So here the refractive index is highest at the center and decreases as you go to the core. So what is the meaning of it? It means that the refractive index will change, right, from one end to the another end, right? So now this is the graded in the optical fiber. You can just see this application of optical fiber. So the optical fiber is mostly used in the communication, Wi-Fi router, line 4, server connector, and so on. Now this with this see with a brief explanation about what we do is that we'll just stop this slide. So we have different applications. We can use this optical fiber in many military application equipments and so on. Sensors, most of the sensors are made up of the, you can see wherever nowadays you go, you talk about sensors, right? So most of the sensors are made up of optical fiber, and optical is what you can say is also used to make the detectors or metal detectors. You can see wherever you go for shopping, right, for going some to airports and so on, you use the metal detector. So there you use the optical fiber. The sensors are made up of the optical fiber. You can just see the schematic diagram there. You can see that you have extrinsic fiber optic sensors and intrinsic fiber optic sensors, right? See the other applications that optical fiber is used to make some decorative applications, lamps, toys, and microscope also. Many medical devices are made from the optical fibers. So you can just see that these are the some devices with which the optical fiber is used as one of the component in the device, right? So now with this we just go for the another important aspect that we'll discuss here. So here what we'll do is that now you can just see this optical fiber here. Again we just will have a very uh, important definition, right, with the other aspect. We can just see the optical fiber. We just start with this fresh the same thing for your further understanding what is actually the meaning of optical fiber. So in the other way, see, we just learn optical fiber is a dielectric, transparent dielectric medium. So here what we say that, right, physically the optical fiber is a thin cylindrical fiber of a glass or transparent dielectric medium. And this fiber optic cable is used for optical communications, waveguides, and made of transparent dielectrics. And definitely it will guide the visible and infrared light for long distances. Now you can just see here the what you can say, um, the structure of the optical fiber. So you can see the structure of the optical fiber. Just now I've shown you. So this is more clear when compared with the other one. So here you can just see this core cladding, and there is a coating here, and you find the outer jacket also and strength of the member. So now core is a, what is actually the meaning of core here? We just discussed very briefly there. So what is actually the meaning of core? Core is a central tube of very thin size which is made up of optically transparent dielectric medium, and the light will transmit from the transmitter to the receiver, and it will have a diameter of 5 to 100 micrometer. And cladding, you can just see this cladding, the optical material surrounding the core, right? And the refractive index of this cladding will always be lower than the core. So just now we discussed what is actually the meaning of refractive index with respect to the light signal, right? So the velocity of the light in the vacuum to the ratio of the velocity of light in vacuum to the velocity of light in the given medium, we say that that is called actually the refractive index. So here we just talk about core and cladding more when compared to the outer jacket and the other thing. Why? Because our signal will travel inside the core, and it will try to at the end of the core you'll find the cladding surface. So there there is a possibility of some loss in the cladding surface also. So what is the basic principle on which the optical fiber is working? You can just see that when a ray of light is traveling from a denser to radiant medium, such that the angle of incidence should be greater than the critical angle. So what is actually the meaning of critical angle here? The angle of incidence for which the angle of diffraction is 90, we say that is called critical angle. So the ray reflects back into the same medium, and this is called the phenomena called total internal reflection, right? You studied in the lower classes also what is actually the meaning of total internal reflection. So in the optical fiber, the rays undergoes totally repeated total number of reflections until it emerges out of the other end of the fiber, even if the fiber is bent. So that is what the special phenomena that is called total internal reflection, right? So this also you studied, right? So the classification of the optical fiber, just now we discussed. See again, for your understanding purpose, we are again discussing the more broadly about the optical fiber modes, right? So the number of modes, that is single mode, SMF, and we say that multi-mode. And when you compare with the refractive index, so we say the step index optical fiber and the graded index optical fiber. You can see number of modes in the single mode just now, SM, single mode, only one mode can propagate through the fiber, and it will have some diameter to 5 to 70 or 100 micrometer. And the difference between the refractive index of the core and the cladding is very small in this case of single mode optical fiber. You can just see single mode is nothing but you can see this particular light ray here, right? It's a single. So step index optical fiber. So you'll find that this mode, right? I'm talking about this mode, right? So this is a single mode optical fiber. This is the core inside which the light signal is passing. So now there will be no dispersion of the light, right? If for a long distance communication, and here the light is passed through the single mode optical fiber through the laser diode. So here we are using the application of laser here. We are transforming the signal. That signal is nothing but it is a laser diode. So when we compare, see, yeah, here again we are comparing with the single mode and the multimode optical fiber. So here in the multimode, you can just see that there is a two signals, right? So this is one of the signal with more reflection, number of reflection, right? And here you'll find that the reflections are decreasing, right? Here, this is exactly total internal reflection. The core diameter of this multimode. So that is, see, first of all, what is multimode? When the signal are more than one, right? Here the light signal is more than one. So the relative refractive index difference is very large when compared to the single mode optical fiber. There is a signal degradation due to the multi-mode. So definitely, see, if you just go for multi-mode, there will be some loss in the signal, right? So it is not suitable for the long distance communication. The single mode is preferably good for long transmission of the signal now. So what is actually here we talk about, it is also the dispersion and attenuation of signal. So here the attenuation means the loss of signal actually. So here on the basis of the diffractive index, you can just see that the diameter of the course in the case of step index and the graded index optical fiber, and also you can just see this single mode optical fiber. So what is a process in which the graded index, that is called the refraction. Through refraction, the light signal will travel, right? Here you can see this is the output pulse. Here this is the output pulse, and here we say that is called the single mode fiber. Now, since we started with the single mode and the multi-mode optical fiber, now we are discussing about the step index optical fiber. The refractive index of the core and cladding are constant in the single index optical fiber, right? Here we are discussing with respect to the refractive index. The light will propagate through it from the what you can say, the shape of that ray. We call that shape of the ray as meridional rays, right? And this reflection at the core and clouding boundary in the case of single index optical fiber. In the case of graded index optical fiber, the type of optical core has non-uniform refractive index, and this will be gradually decreasing from the center towards the core cladding interface. The cladding has a uniform refractive index, and the light rays propagate through it in the form of helical rays. The form of rays, the shape of that particular ray light signal, we say that is called helical ray, because and they will never cross the fiber axis. What is a fiber optics exactly? You can see this again. See, this is actually a center. See, this is, we'll call this as fiber axis. It is passing through the center. Here also, the passing through the center, we say that is called fiber axis. Now, optical fiber communication system. So where actually this is the uh, optical fiber will be used, right? So in the communication system, with respect to the communication system. So now, so here you will find that difference of optical fiber communication system. We are not going in detail that what is the optical fiber communication system. When you go to the next semester, you will understand what is this communication system is all about. So attenuation in the optical fiber, you find that the signal will be attenuated. What is the meaning of attenuated? Attenuation is the loss of the signal. Definitely, you will find that there will be some loss in the signal, and that loss in the signal can be measured with respect to the attenuation. So here, attenuation in the optical fiber take place due to the different elements, which with we take the help of that elements to pass the signal from one end to the other end. So you can just see this. This is the original ray. I have shown you this is original ray, and you will get some. There will be some loss in the signal, and you just amplify it, right? Then you have an amplifier here. 0.1. See, you just compared it, right? This 0.1 is the original signal, and this is transmitting medium, and this is 0.2 where the signal is got some attenuation, the loss of the signal, and by using the amplifier again, you just amplify it, and we got this particular amplified signal. Now we say this is called different attenuation process. So here, what are the advantages? Due to its bandwidth, it is utilized immense bandwidth. We can have, for example, you just take the cable channels. You find you can at a time you can view different types of the channels, right? Hundreds and 200s of channels, right? For example, right? So that is actually residing in a you'll have a frequency range, that is, we'll call that as bandwidth, and there will be very less loss when compared to the normal metallic cable or copper coaxial cable. They are very small inside, lightweight, high signal security. Just now we just discuss about this advantages of the optical fiber. Now with this, we can say that we just discuss the what is actually the optical fiber, and how this optical fiber has been classified depending upon the diffraction index profile, the step index, and the graded index optical fiber. Again, when we talk about the modes, right, we just discussed about single mode and the multi-mode optical fiber. Now, again, we discuss about the what you can say, the what is the meaning of attenuation. Definitely, there will be loss in the signal. So we just discuss what is attenuation, and we discuss the advantages of optical fiber. Now we just see the video. What is actually the optical fiber is made of our double, how they work, right? And so we just see this video, right? And now uh, you can just see this. We'll like a video of this.
I find this a fascinating object. It's a fiber optic cable for a stereo. If I shine this laser pointer down the cable, it guides the light out the other end. These cables are used to connect our world today and are capable of transmitting information across countries and oceans. But first, let me show you how it works. I have a bucket that I've modified with a window in front. And on the other side, I put a stopper in this hole right here. I have a bottle of propylene glycol with just a little bit of creamer in it. A ring stand, and of course a laser pointer. Keep your eye on this plug when I turn out the lights. That's wonderful. The light follows the liquid flow all the way to the bucket. Amazing. It does this because of total internal reflection. As the light enters the stream, it is reflected as soon as it hits the interface between air and liquid. You can see here the first reflection, and then the second, and the third. This occurs because there's a difference between the index of refraction of the guide material, here propylene glycol, and the outside, air in this case. Recall that any time light strikes a surface, it can either be absorbed by the material, reflected from it, or pass into and through it. The latter we call refraction. It's easier to see from a top view. Reflection and refraction can happen at the same time, but if a light ray hits the surface at an angle greater than the critical angle, it will be completely reflected and not refracted. For this propylene glycol and air system, as long as a beam hits the surface at an angle greater than 44.35 degrees, measured from the normal, it will propagate down the stream via total internal reflection. To create this same effect in an optical fiber, engineers create a core of glass, usually pure silicon dioxide, and an outside layer called cladding, which they also typically make from silicon dioxide, but with bits of boron or germanium to decrease its index of refraction. A 1% difference is enough to make a fiber work. To make such a long, thin piece of glass, engineers heat a large glass preform. Its center is the pure core glass and the outside the cladding. They then draw or pull a fiber by winding the melt onto a wheel at speeds up to 1,600 meters per second. Typically, these drawing towers are several stories tall. The height allows the fiber to cool before being wound onto a drum. One of the greatest engineering achievements was the first ocean-spanning fiber optic cable. Called TAT-8, it extended from Tuckerton, New Jersey, following the ocean floor over 3,500 miles until branching out to Whitmuth, England, and Ponmarsh, France. Engineers designed the cable carefully to survive on the ocean floor. At its center lies the core. Less than 1/10 of an inch in diameter, it contains 6 optical fibers wrapped around a central steel wire. They embedded this in an elastomer to cushion the fibers, surrounded it with steel strands, and then sealed it inside a copper cylinder to protect it from water. The final cable was less than 1 inch in diameter, yet it could handle some 40,000 simultaneous phone calls. The essence of how they send information through a fiber optic cable is very simple. I could have a prearranged signal with someone at the other end. Perhaps we'll use Morse code, and I just block the laser so that the person at that end sees flashes that communicate a message. To transmit an analog signal like voice from a phone call along the cable, engineers use pulse code modulation. We take an analog signal and cut it up into sections and then approximate the wave's loudness or amplitude as best we can. We want to make this a digital signal, which means discrete values of loudness and not just any value. For example, I'll use 4 bits, which means I have 16 possible values for the loudness. So the first 4 sections of the signal could be approximated by about 10, 12, 14, and 15. We then take each section and convert its amplitude to a series of ones and zeros. The first bar of value 10, when encoded, becomes 1, 0, 1, 0. We can do this for each section of the curve. Now, instead of looking at the green waveform or even the blue bars, we can think of the signal as a series of ones and zeros organized by time. And it is that sequence that we send through a fiber optic cable, a flash for a 1 and nothing for a 0. Of course, the exact method of encoding is known at the receiving end, so it is a trivial matter to decipher the message. Now, you may be wondering how a laser pulse can travel nearly 4,000 miles across the ocean. It doesn't without some help because the light will escape from the sides of the fibers. Look back at our propylene stream. Here's how the light attenuates as it travels. You can see here a narrow beam in the bucket that broadens a bit when it enters the stream, and then after the first bounce, the beam leaves even broader than it entered. That's because the interface with the air is uneven and the rays that make up the beam strike at slightly different angles. When that beam makes its second reflection, those individual rays diverge even more until by the time it reaches the third bounce, many of the rays are no longer at the critical angle and can exit from the sides of the stream. Here it happens in a few inches, but in a cable like TAT-8, the signal travels a stunning 50 kilometers before it needs to be amplified. Absolutely amazing. I'm Bill Hemmick, the engineer guy.
So with this, let's conclude our talk, today's talk, right? So here we just discussed about the optical fiber. In the next class, right, we'll just see the optical fiber applications also we discuss, right? So with this, we have just completed our major portion of the unit 5. Thank you, everyone. Thank you for your patience.